Today's lesson is our very first lesson in calculus, and it is simply introducing calculus. It's kind of a big idea introduction of how calculus all started. I'm going to start with reviewing average rate of change. So you have learned this before. I'm going to give you the formula and give you a quick rundown of what it is. So if you were looking at a function, and we're looking at the closed interval from point A to point B, and we want to find the average rate of change. That's basically just saying if I draw a linear line that connects those 2 points, what is the rise over run, or the change in y divided by the change in x. So here we have this formula, f of b minus f of a over b minus a. This is just a fancy way of saying this is the change in our y values, and this is the change in our x values. These are the x values that we're plugging into our function to become y values. This formula is often referred to as the difference quotient formula, and it's when you're showing your work, you have to make sure that you're showing the difference and the quotient. We'll do a full example of this later in this video. So this is just a review of average rate of change, and sometimes we even shorten that and we refer to that as AROC. All right, so now let's look at this function. So it's the same function graphed twice. This negative x squared minus 2x plus 3. And we're going to talk about the difference between average rate of change over an interval and average rate of change at an instant. So this at an instant is where calculus comes into play. So the idea of over an interval, this is what we were just talking about, average rate of change. So over an interval, we connect this line where we're connecting 2 points over an interval is called a secant line. So a secant line is helping us find the average rate of change. So one thing to put this into perspective, like that change in x is often in the real world application, it's our time. So it's change in time, something that's happening over time. But now, this idea of average rate of change at an instant. That would be like, at this exact point, what is the average rate of change at that instant? So it's not over a change in time, it's at that instant. This, when we draw a line that goes through that point, this is called a tangent line. We will hear this word lots and lots this year. Okay, so let's explore these two concepts a little bit more. So back in Algebra 1, you learned how to find the slope between 2 points, and you learned this formula. M is your slope, and you did the y2 minus y1 over x2 minus x1. These two formulas communicate the exact same thing. So this is what you first learned, so that helps your brain. That's just what we do in Algebra 1, and then this is the more like formal way of writing it for calculus. So let's find the average rate of change from -3 to -1. So that's that same secant line that we've already drawn. And another way to do interval notation is from -3 to -1. So if we're going to formally show our work, we're going to look at the function at -1 minus the function at -3 over -1 minus -3. Notice how these match up here and these match up here. So f of -1 is 4, whether you plug it in or just look at your graph. 4 minus 0 over -1 plus 3, which is 4 over 2 equals 2. And this makes sense if we go back here, go back to algebra 1, rise over run is just, it's up 2 over 1. Okay, practice the next example on your own. Write it down, pause the video, and try it. And I want you to practice showing proper calculus work. And you should get -1. So that was slope between 2 points, which is the same thing as average rate of change. And now we're going to explore that idea of this instantaneous rate of change. Okay, so I'm going to draw that same tangent line at -2. So the key thing with this tangent line is the only point that it touches on this parabola is this point right here. So what is that? What is like the rate of change of that line? Which it's hard to tell because we don't have a change of x if we're looking at something at an instant. But we can make estimates of this. We can, let's see, what about between like these two intervals right here? I connect those. I could find the average rate of change from here, and it's maybe close to that. That's not very accurate. Okay, can we get closer? What if we did these two? Get closer. And how close can we get by just making that interval smaller and smaller and smaller? So if we make that change in x really, really close, really, really small, I can get a really good estimation of this rate of change of this tangent line. So at -2, the x value -2, the y value is 3. So what I want to do is I want to get an interval around -2, but as small as we possibly can. So we're going to choose numbers very, very close. So let's choose -2.01 and -1.99. And we can plug these in to the formula and get our y values. And in class, I'll show you all kinds of calculator tricks this year that can help you with these numbers when they get kind of annoying. But I'm just going to do this for you. Is when I plug in -2.01, the y value is 2.9799. And when you plug in -1.99, you're going to get 3.0199. So now let's find the average rate of change of this really small interval. So here's our difference quotient of our y values, x values, and we will get 0.04 over 0.02, which equals 2. So this would be the estimate of the rate of change of this tangent line. And similar to average rate of change, AROC, instantaneous rate of change, you will hear me say IROC sometimes throughout the year. And this idea here is finding that change at an instant is kind of the birth of calculus. So there is your introduction of the year. And we'll come back to this topic much more in Unit 2, actually.